Hey, welcome. We're looking at 6.7 task, starting to look at using radians here. There's an archaeological site and they've got concentric circles. So here's a possible picture of that. They have 10-meter intervals. So you would go 10, 10, 10-meter intervals. And they have 16 stakes per circle. And then they go ahead and create that. And the idea is to try and locate the position of these stakes. And the idea Veronica had was to first set them up in the smaller circle, and then from there you can figure out where they'll be on the larger circle. And you can do that by just drawing a line out from the center that goes through that second stake, and the point where it intersects the next circle will be the third, and the point where it intersects the next will be the fourth. So that in that way, because the angle is really the same, then you can figure out where those stakes would go. And then Veronica says they should stake out a circle with a radius of 50 meters. And it needs to be 22.5 degrees around the circle for her next stake. But the question is, how far is that? Like, what is the distance there? So that's really saying arc length. So Veronica says she'll find the distance, the arc length, by setting up a proportion using degree measurements. Uh-oh. Okay. And so a proportion, you might say here, you might say 22.5 divided by 360. Okay, that ratio is going to be the same as the distance to the circumference, 2 pi r, 2 pi times 50. And so you could do it as one way to calculate that distance. Another way you could do it is Alice, where they should take 1/16 of the circumference. So here is 1/16 of the circumference. Now notice 22.5 divided by 3060 is the same thing as 1/16. The third one is using radian measures, and radians are arc length divided by radius, how many of the radius it is around the circle. So the arc length is going to be radius times the radians. So this is the formula you have here. So this, let me do it on here. So this S represents the arc length. That's the distance. The R is the radius. And this is the angle measured in radians. Okay. So, for example, you could do the radius times, there's 2 pi radians. If you're only going 1/16 of the way, it would be 2 pi divided by 16, or pi over 8 radians. Okay, and so Javier likes locations of quadrant 1, and then you can just use rotations for the rest, and that works because we have 16 stakes. 16 divided by 4 is 4, so you could do 4 in each quadrant, and then you could rotate it. And so what you're going to do in this problem is you're trying to find location of stakes in the first quadrant, as well as the coordinates and the arc lengths for each. So the coordinates are the location, and the arc length is the distance. So let's look at how we could do that. First thing, let's review in terms of the radians. So looking at this, if this is your starting point, you've got 1 radius, 2 radius, 3, 4, 5, 6. You can see it's a little bit more than 6 radius around. In fact, there are 2 pi radians in a circle. And that is the same thing as 2 pi r, which is the circumference. So there's 2 pi in a circle. So we'll use that idea here. So if we want to look at, for example, this first stake here, it's 1/4 of the way of the quadrant, or 1/16 of the entire circle. We can do 20 as the radius, so I'm going to calculate this one right here, times theta, which is 2 pi but divided by 16, right? It's only 1/16 of the whole thing. It's 1/4 of 1/4. So 2 pi 16 is really pi over 8. So that's going to be pi over 8 radians across. And if you multiply that out, it's about, that arc is about 7.85. So again, we're taking a portion of the whole circle, which is 2 pi r, but we're only taking 1/16 of that, and so we're taking pi over 8, and we're multiplying it times the radius because it's the arc length, and that gives us approximately 7.85 for the distance. Now we can also calculate the location of this point using our trig functions. So because we know that, and you can kind of see here, let me do it in blue here. This is the triangle that we're working with here. Okay. And so the x value of this triangle down here, we can say that the cosine of theta is equal to adjacent over hypotenuse, or x over r. So cosine is adjacent over hypotenuse, and because of that we can say that x is equal to r times the cosine of theta, which, plugging in values for r of 20 for a radius and plugging in pi over 8 for theta, gives us approximately 18.48. So it's 18.48 over, which kind of makes sense because it's almost 20. And then we can also say that the sine of theta is y over radius, or opposite. So if this is theta, sine is the opposite over the hypotenuse, which is radius. So therefore y is r sine of theta. R is 20, theta is pi over 8, we get approximately 7.65, so that's the y value. So now we have an xy coordinate, 18.48, 7.65. We also have a arc length of 7.85. Now we notice with these concentric circles, the first one goes out 10, the next one goes out 20. When we look at the numbers, we notice that the arc here was 3.93, and the arc over here was double that, 7.85. We also notice that the x value of 9.24 was doubled to the x value on the larger circle, and for the y value 3.82 was also doubled, and that's because the radius was also doubled.